is is done to see. Basically, the objective is to calculate the coefficient of friction of the road by uh, starting a vehicle at 40 miles an hour and bringing them with the wheels locked to see how long it takes and what kind of deceleration it experiences. This is the kind of test that they want to do, and that is, as you can see, how the acceleration test 3 seconds from stop, and of course they have the vehicle model and so on, and every second they're recording the data of what that instrument is telling them every tenth of a second, although the system is capable of sampling a much higher rate than that, probably 100 times a second. So there's another view of the accelerometer as it was mounted on a police car. They had two accelerometers, that one, and you see they're just checking the tires here, but let me see. Let me go back to the accelerometer right here. This is where you want to see. So this is an accelerometer that is mounted on the windshield of a police car, and we are going to do a test that bringing the car to a stop from 40 miles an hour with the wheels locked, measure the deceleration, the distance, and calculate the coefficient of friction. That's another view of this. And they used two, a B3000 and a BC4000. Okay, so that is, let me just see if we can play the video here, which is what is important here. This is we see this is the police car as they were going to do the test, and again this is during the test, so the readout is, we cannot see it very well in there, but that's where we see the readout. But now let me show you this video in here. So you begin to see exactly how it goes, and in here let's try it again. We're gonna play it again. Okay. Okay, so that was one test. We're gonna play this other video. You begin to see that they probably need to change the tires after that. And this was the test inside the car. And you can feel the deceleration is really high in there. But that's the objective. Now, what I want you to know and want you to have is a model that was done with a police car, and here we go. This is a working model 2D of the same test. So we're gonna see a vehicle that has been placed. Here's where the car is. Yeah, this is the car starts at 40 miles an hour from begin, and we're going to bring it to a stop in here. Let's try to see. We'll see it both ways, from the beginning or at the end. So in here we go and get started, and you can see, let's do a reset. I'm gonna bring it over here a little bit more so that we can see the stopping part. Okay, so Let's hope that we don't have a, obviously there is a little problem here with it. Okay, we're back and we're gonna run the vehicle here, and there it is. So you can see exactly how the forces develop as the car comes to a stop. This is the same thing as we see on this graphics. So if we can perhaps do this, reset the conditions. We want to look at the plot maximum. I think is we want to do. I think was 4. Yeah. And then you have the other one that we want to see also is 4, right? 4 seconds. That way we have it right. And we have one more. This is 3 seconds in time. And that's the acceleration. Okay, let's give it a shot. Run. There we go. Okay, let's analyze this. And perhaps I'm going to go, this program has the ability to go back a little bit in time, you see. So we can analyze in a slow motion now what's happening. Let's take a look here. See, it's at 16 miles an hour, 15, 14, 13, 12, 10, 9, all the way when it finally, you see how it changes the reactions on the tires at the end? That changing the tires at the end produces a jerking motion that shakes the car. So, yeah, and then finally, you could see the velocity, it comes in about 62 feet. The velocity in here from 40 miles an hour down to 0. And the acceleration, you can see we have a settling down time, and this is the acceleration. See, in here you have the accelerations in miles per hour per second. Perhaps you can translate this from miles per hour per second to feet per second square, and then you'll see that this is, and then related to 32.2, then we will have the ratio of the acceleration with respect to gravity, but that would be the measure in there. So if you go back, the idea is, in here you see how the acceleration is, this green vector is the acceleration. Let me just go a little farther back. You can see the vectors there. The acceleration is minus 17.7 meters per second. That's what this is. And then you have the reaction on the front tire is big. This is the 2,800 pounds compared to 1,000 pounds on the back. And at this point it's at 19 miles an hour. And you can see the friction forces are acting in the opposite direction as well. So if you reset and then run, this is what you see. So we have the ability to also look at the numbers in here. See, 62.96 feet at 0 miles, of course, but you couldn't make it go back. See how we measured at every instant of time the distance and also the velocity and the acceleration. So that's what that test is. But with this, because you are basically converting the kinetic energy into work by friction, then you have 1/2 of mv squared equals to mu mg times the distance. So if you know these variables, you can find out what the coefficient of friction is, this mu. But the computer does it automatically here. And obviously in this case, we have an acceleration of, could you please convert 17.7 miles per hour per second to feet per second squares? Or we can do this a ratio of gravity.
You could do go to world, the file, go to world. I'll go to world right there.
Yeah.
And then click units. Maybe it might be EU.
No, it's we need to convert it in the English system.
Okay.
But in any case, this is the I just wanted to show you that the program with the blue vectors, that's the velocity, with the green vectors, the acceleration, and with the red vectors, the forces, that you can control all three of them in here. This test that we have in here reproduces exactly the test in the real life. So we have had good success with it.